Welcome all. Today we are going to solve some numericals of Chapter 13, Elasticity. First numerical that we are taking is question number 3 of your textbook. The copper wire has a length of 2.2 meters and the diameter is given as 7 into 10 to the power minus 4 meters. So we convert it into the radius, which will be 3.5 into 10 to the power minus 4 meters. A weight of 5 kg is suspended. So the weight is going to be 5 into the value of g is given to you as 10. Young's modulus is 1.25 into 10 to the power 11 Newton per meter square. You have to simply calculate the elongation in length. So using the formula for the Young's modulus, which is equal to stress upon strain, we get the value of delta L, that is the extension, as the weight, which is mg, into the length divided by area of cross section multiplied by Young's modulus. Substituting the values, we get the answer as 2.28 into 10 to the power minus 3 meters. Next numerical that we are considering is question number 7. In this, the length of the wire increases by 8 millimeters when a weight of 5 kg is suspended from it. Now, if the other things remain same and the radius of the wire is doubled, then what will be the increase in the length? Now, using the formula of Young's modulus, we see that the extension in length is inversely proportional to the square of the radius. So, taking the ratio, we get the new extension in length when the radius is doubled and all the other things are kept constant as 2 millimeters. Question number 15. For steel, the breaking stress is given to you as 8 into 10 to the power 6 Newton per meter square, and the density of the wire is 8 into 10 to the power 3 kg per meter cube. You have to find the maximum length of the steel wire that can be suspended without breaking under its own weight. So if you see, the stress is equal to the force upon area, which is the weight mg divided by area, and density is mass upon volume. We've used volume as area of cross section multiplied by length. Now multiplying the density with the value of g, we get it as stress upon the length, and therefore the length is stress divided by density into g. So substituting the values, we get the length of the wire as 100 meters. Let us now consider question number 16. In this question, a body of 10 kg is tied to one end of a wire of length 0.3 meters and is rotated in a horizontal circle. The area of cross section of wire is 10 to the power minus 6 meters square, and the breaking stress is given to you as 4.8 into 10 to the power 7 Newton per meter square. Now you have to calculate the maximum angular speed. Now for the maximum angular speed, the tension in the string or the force should be equal to the centripetal force, which is equal to mr omega square. Force is equal to the stress upon the area of cross section, and substituting the values, we get omega square is equal to force upon mr, which comes out as 4 radians per second. The last question that we are considering for today is question number 27. The Young's modulus of brass is 10 to the power 11 Newton per meter square, and the area of cross section of the wire is 10 to the power minus 4 meters square. The length is 0.1. When it is compressed along its length with a force of 10 kg weight, you have to calculate the increase in energy. Now, the energy is equal to half of stress into strain multiplied by the volume. Now, from here, what we've done is that the strain is equal to stress upon Young's modulus. So the formula now changes into half stress square into volume divided by Young's modulus. Substituting the values as given, the answer comes out as 4.802 into 10 to the power minus 5 joules.